Hi, I'm going to talk about the proposed CLK AC DC charge pump for magnetostrictive vibration energy harvesting. Uh, this figure indicates the IoT edge devices with energy harvesting. Here's the things, internet, and cloud. The things connected in parallel to internet. Each thing has a sensor and RF chip. The sensing circuit can sense the surrounding temperature, the surrounding humidity, or surrounding pressure, and so on. And that information can be transmitted through RF to internet. To eliminate the batteries from things, and so magnetostrictive energy transducer can convert from vibration energy to electric power for the sensing or RF chip. So vibration energy transducer generate the AC power, which has 0.5 volt peak, whereas the sensor and the RF chip required DC 2 volt with a few microwatt. To convert from this AC voltage to this DC voltage, the charge pump is required between the two, which can be integrated in sensor IC. What is the application? This is one example. And this kind of sensing circuit is attached to the ferry engine to monitor their healthcare. So before the ferry engine is fully broken out, the ferry engine generates the abnormal vibration. So before the braking, this sensing device can catch that indication before fully breakdown. Then that sensing circuit can detect that abnormality to transfer that information to the internet. So the aim is the elimination of replacement cost for batteries. This kind of energy harvesting system is considered. What is the issues to be addressed in conventional AC/DC charge pump? Because of very low vibration frequency, ranging from 10 Hz to 1 kHz, the charge pump is needed to be placed on the printed circuit board because the charge pump output current I-out is approximately proportional to the frequency of the input power times the capacitor of the charge pump circuit. And because of f of 10 to 1 kHz, the C capacitors number is required to be about a microfarad order to output microwatt power. There is no such capacitor which can be integrated in one IC when the capacitor size is microfarad order. As a result, the capacitor must be chip capacitor, and which needs to be placed on the printed circuit board. To be worse, because the charge pump requires to have the number of stages of about 10 to generate a 2 volt. The number of chip capacitors and diodes about 20. As a result, the conventional charge pump solution requires large circuit size and very high cost. However, we want to distribute many sensing elements for the IoT world. The cost is the number one priority to be addressed. So how we can do that? Here's the concept of our proposed CLK AC DC charge pump. So to have micro ampere order output current with the picofarad order C, we need a much higher frequency, which can be done by integrated oscillator, because the on-chip oscillator can run at 10 MHz, even at 0.5 volt. So by doing this, I mean, if you implement full wave rectifier and on-chip oscillator and charge pump circuit, and in the same chip or in the same sensing circuit, you can get just only require the 0.1 millimeter squared of silicon. This means that all building blocks can be integrated in a single sensor IC, which contribute to very low cost and small form factor, because very large charge pump are fully eliminated with this solution. So to confirm this concept is effective, we fabricated the circuit in a 65 nanometer 1 volt CMOS, which provide the low VT transistors. We successfully integrated with all building blocks into small size of 0.1 millimeter square. And we evaluate the circuit using the actual magnetoselective energy transducer, which was provided by Ueno Labo at Tanzawa University. And this lead portion is the vibrator, which can be adjustable for the accelerator and vibration frequency. And we connect the circuit with this magnetoselective energy transducer, and also connected to the oscilloscope to measure the internal signal. The result is like this. You see the V1, the V2, which is the output of 2 terminals from magnetoselective energy transducer. This input is transferred as fully rectified voltage like this, which is input to an on-chip oscillator. Here's the output from the oscillator. And if you zoom up, you see this kind of high-low transition, because this is about 1K hertz, whereas the clock frequency is 4.8 megahertz. And this orange lines shows the output voltage, which is about 2 volt plus a small ripple. And as you see, the fabricated circuit is confirmed with the functionality. Here's the estimate of power distribution of conventional and proposed circuit. This arrow shows the power from energy harvester, but most of them is not effective. I mean, even the energy harvester generate this power, the very small amount of power can be input to conventional charge pump. On the other hand, the clocked AC DC charge pump can input more power than the conventional circuit. You get the much more higher power with 4 microwatt. If you place the charge pump circuit with the conventional method, then you only get output power of an order of nanowatt, which is 500 times lower power. So, I mean, this shows that the clocked AC DC charge pump can generate the microwatt order power from the same power of energy harvester. Another interest is the dependence on the frequency of a vibrator. Because if your circuit can only generate the power which is significantly dependent on the frequency of the vibrator, you have to fabricate the individual the circuit per individual the vibrator. In that situation, the design cost and the production cost must be much higher. However, this circuit has very flat across very wide range in the vibrator frequency. Once you design a certain case, design the circuit under a certain frequency, that circuit can operate even at very different vibrator frequency. This indicates that you can get further cost reduction with the proposed circuit. In summary, we designed a full integration of power conversion in microwatt sensor AC, which has very small form factor and significantly power reduction solution for vibration energy harvesting. And the experimental result shows a fundamental circuit operation and output power is kept constant even with different transistors with different resonance frequencies. Thanks.